morning and welcome to a new webinar of AFM Cluster. Today's topic is reducing risk and saving costs by testing programs on PLCs by our partners in Shitazo. My name is Narua and I'm part of AFM Cluster team for today's program, and I'm going to do a short presentation of the cluster. Then Markus will give his presentation about reducing risk and saving costs by testing programs on PLCs, and then we'll close the webinar with questions and doubts you may have. And AFM Cluster is the first association that borns in Spain, and nowadays we have more than 800 companies and more than 100 partners. And the cluster is made up of 7 groups representing machine tool and components, additive manufacturing, cutting tools, machining, cutting, boiler making, automation and robotics, hand tools, and the last group will be startups for advanced manufacturing. I also wanted to talk about Joint, and the first industrial website created by AFM Cluster. It's a job and website free of charge, and that links the candidate with the hiring company. And I invite all of you to discover more at joint.es. This is the short presentation that I wanted to make. And now I give way to Markus, a software developer at Shitazo.
So I'm going to share my screen. Welcome everyone to my presentation today about reducing risk and saving costs by testing PLC programs. I'm Markus Klegge. I've been at Shitazo as a working student for a couple of years now, and now I'm a full-time software developer and a member of the IT/OT community at Shitazo. I completed my master's thesis at the University of Applied Sciences in Münster in northern Germany in collaboration with Shitazo and one of our clients, about testing PLC software during the development process using different techniques from software engineering. And after a short introduction, I will tell you about the different software engineering techniques that I used, and also about the pilot project I did for my client. And after that, I will share my results and findings. So to understand the motivation for the project, here's a short brief history of software testing. So in 1945, the team of Grace Murray Hopper at Harvard coined the term computer bug and also debugging after they found a moth, like a physical moth, in their computer, leading to errors in their programs. In 1979, Glenford J. Myers introduced the separation of testing from debugging, which was coined by Grace Murray Hopper, in his book, The Art of Software Testing, and specifies a standardized terminology that we still use to this day. In 1991, Mercury Interactive launches WinRunner, which is a record and playback tool for testing graphical user interfaces, where you record the clicks that you're doing, and then you can automatically let them repeat to have some kind of automated testing. And similar tools are still used in web development. In 1997, Kent Beck and Eric Gamma developed and released JUnit, which is a unit test framework for Java using automated tests. And in 2001, the Agile Manifesto was published, which is a book by, I think, 17 people, which emphasizes iterative development and testing and inspired practices like test-driven development and behavior-driven development. So as you can see, until the 1990s around there were only manual tests. And with the release of WinRunner, the era of record and playback tools started. And as of 1997, with the release of JUnit, sophisticated test automation frameworks are in use in software development. And the development and usage of software testing techniques and tools led to improved error detection, lower costs, higher software quality, and in turn, also better customer satisfaction. And the current state of testing and automation technology in the machinery sector especially is mainly performing manual tests on the physical machine. So basically, as it were in software development in the 1990s. And the result are long testing times and extra work, longer downtimes during first startup of the machine, longer commitment of employees, and overall high costs. The idea of the project was to transfer the tried and tested techniques of software development to the world of automation technology. To distinguish the differences between automation technology and software development, we can look at their context and their role. So automation technology is the control of autonomous technical processes and physical devices in industrial machines. It is part of operation technology, and also called OT for short, which is using systems to detect and cause changes in industrial operations through monitoring, controlling devices, processes, and events. And that in turn is part of electrical engineering. So the study and application of electricity, electronics, and electromagnetism toward the development of electrical system and devices. On the other hand, software development is the creation and application for digital management, processing, and transportation of data. So everything that has to do with digital data. It is part of software engineering, which is the systematic application of engineering approaches to that development, and also the maintenance and the testing of software to ensure reliability and efficiency. That in turn is part of information technology, or short IT, which is the use of computer storage, networking, and other physical devices, infrastructure, and processes to create, process, store, secure everything that has to do with electronic data. So here we can see the difference of IT and OT, and these are the two worlds that are converging. And even though in practice these technologies are not as distinct as they are shown here, they have some overlap, but they are not inherently the same. However, with my project, I'm showing that the techniques of software development are still applicable to the automation technology, even though they are different and the tools are different as well. Now, if I'm starting with the software engineering techniques that I used in my project. First and foremost, the test strategy, which for software engineering is defined in the ISO, so the international standard 29119, which defines a generic process for software testing. It offers information and guidelines on different aspects like different test approaches, metrics, regression testing, artifacts, test data, and so on and so on. And a test approach, which is arguably the most important aspect, defines the techniques. So how am I testing, the test types, why am I even testing, and the test levels. So what am I testing? Technique means, am I testing statically or dynamically? So am I executing the code that I'm testing or not? Am I just looking at the static code without executing it? It's also about if it is manual or automatic testing, for example. If I go through by hand and look at the code and do the tests, run everything, or if they are automatic testing, which is very important. And thirdly, it's also about if it is specification based. So is what I'm looking at a black box? I don't know what's going on in there. Or is it a white box? Or as a structure-based test, I know what the structure of the program or the product that I'm testing looks like. The type defines why am I testing? Am I testing for functionality, for efficiency, for usability, or what am I testing for? And the test level is basically the test object. What am I testing? And what is the level of integration with other components in the overall system? So how connected is it to other units? And to visualize the test levels, in 2009, a programmer named Mike Cohn popularized the test pyramid that has since been developed a bit further, and it looks like this. So the test pyramid shows the different kinds of tests according to their level of integration with the surrounding system. It shows how many tests should generally be written in each level, as well as the corresponding testing costs. And from the bottom up here, you can see the first are unit tests, which is testing the smallest possible unit in itself, while ignoring influences to and from other components completely through a technique called mocking. And mocking means using placeholder objects for real components that don't exist yet, or that are hard to model, or that have bad performance, or that we just want to ignore just for isolation of the unit that we want to test. And the developer can control the behavior of the mock object completely. So they have complete control over the test, basically. Next up, we have the integration tests, which are showing which is testing the interaction of different components with each other to ensure that they're working together correctly. And next step are the system tests, which is testing the entire system in an environment that is very close to the actual production environment. And all the components are working together, and we see that inputs and outputs of the system are processed correctly. And lastly, at the top, we have the acceptance tests, which means we're testing the entire system. Or basically not we, but the stakeholders or the users, or the end users are testing the entire system to ensure compliance with the initially stated requirements. So does our product or our software do everything that was initially required from it? And the lower level of integration, the tests here, the unit tests are easier to write. And it's easier to write well-structured and meaningful tests as well, which is why the number of tests is very large. So here you can see the number of tests, and the number of tests is large. But because the number of tests is large, they should also be automated to save time and money. And as the testing costs rise with each level of the integration, which you can see here, because more and more components are taken into consideration, the number of tests that should be written lowers as well. So we can see here at the top of the pyramid, we have manual tests, but mostly everything below should be automated as much as possible, just to keep the cost down. The next software engineering technique is code coverage. So code coverage is a tool to report which lines of code are tested in a software. It provides information about the overall ratio of tested to untested code. So if I have 100 lines of code and I can see for each line if it is tested or not, and I see 70 lines are tested and 30 are not tested, then I have a code coverage of 70%. And that enables developers to write purposeful tests for so far untested code, because I can specifically see which lines have been tested and which haven't. And code coverage, all in all, improves code reliability, because I know my code has been tested and it should work. The next engineering technique is version control. And this is very important in the context of automated testing. Version control is introduced with tools that record changes to a file over time, including what was changed and who changed it and when did the change happen. So it's very easy to see the development of a certain file, for example. It is possible to recall a specific version later in order to identify these changes, why they were made, and because I can recall them, I can also, if I want to, revert all the changes and maybe fix the code because in the meantime a bug was introduced. Changes are pushed to the repository on a server, which provides backup of all the historic versions of the files. And that enables easy collaboration because multiple people can work on the same project simultaneously without overriding each other's work. So for example, this developer here can write some code, push it to the repository. These two can pull the code, can have the identical state of the program as this developer. They can develop further and can always push and pull to the repository. And if the same file is affected by changes from multiple people, the changes are then merged. So one has in the server we always have one conglomerate of correct changes, basically. Next up, we have continuous integration and continuous delivery or deployment. So there's small differences, but basically means the same thing. In short, that's called CI/CD. And continuous integration is the developers continually committing written code and tests to shared repositories. So as I explained earlier, and then triggering an automated build and testing process. So testing is done automatically. And continuous delivery or deployment means the automatic release and deployment of the program after successful tests and then monitoring during production. This means that tests are run continually with each iteration to make sure that changes to the code do not break the system in production. And yeah, for this, as I said, all the tests are run. So not only the tests for the components that have been changed in the last version, but all the tests that are available. And this ensures that changes in one component cannot cause bugs in another component. This is called regression testing. And it reduces costs through an automatic build and test and releasing process because less people have to manually, with hands-on, take care of this because the CI/CD does this. It reduces the risk of bugs and downtimes due to regression testing, and also improves system stability and collaboration. And CI/CD pipelines are the tools that are used for implementing this process. And yeah, for each new version and the version control, the build tool is then executed to get a runnable version of the software, which is then automatically tested with the tests that the developer has written before. And if bugs are found during this testing, the developer fixes them and writes new unit tests for that test case to make sure they cannot occur again. And so with these iterations, the software is always tested and the reliability gets better and better. Now for the pilot project, we used the PLC program for this weighing and dosing machine that you can see here. It has a main scale up here and a smaller subscale that is leading into the bigger main scale for smaller quantities of materials, as well as for storage containers that are at the bottom. And they all possess a mixing device with a motor, and they're connected by pipes and valves. And the machine and its PLC program use Siemens technology for hardware and software, so I mainly focused on that. The goals of the project were creating a test strategy for this machine's PLC program based on the ISO standard 29119 that I explained earlier. And based on that, other goals were implementing unit testing, integration testing, and system testing. So the pyramid that I showed, test automation, version control, the CI/CD pipeline with regression tests, and code coverage for the PLC program of this machine. So basically, all the techniques that I explained, I wanted to fit in my pilot project. So for unit and integration testing of your PLC code, you first need to be able to write tests for your PLC code. And in the Siemens world, this means that the code itself is written in the Totally Integrated Automation Portal, or in short, TIA portal. And in order to be able to write tests, you need to install the TIA portal Test Suite Advanced. This then adds a new tab to the project navigation where you can add test files and also style guides for static code analysis. Style guides are just, you can add different rules and naming conventions and conventions for metadata that then are checking the code that's in your different networks. And Siemens provides a recommended style guide on their website that can be imported into your project, and that makes it fairly easy. To execute the PLC program and then run the tests, the PLCsym Advanced is used on the right. PLCsym Advanced creates a virtual PLC on your computer that behaves like a real physical PLC, but you do not need any additional hardware to execute the program on this. Tests are then written using the arrange, act, assert pattern. So let's say we have this function A on the left with input 1 and input 2 and one output. And a normal test would look like this on the right. So you have surrounding each test, you have the step and end step keywords, which just tell the program that in between there is a test, and also you can set a name for your test because you will have multiples. Then in the arrange stage, the test parameters are set. So the inputs are set to whatever you need for the test, and the output is set to false in this case, because afterwards we want to see if it's true, and we want to make sure that before the test, it is not true already. So we set it the opposite of what we expect, basically. In the act stage, the PLC is then run for a number of cycles or a set amount of time, just to then be able to observe in the assert stage the test result. And yeah, in this case, if the output is true, that means everything works correctly. And if the assertion is correct, the test passes, and if it's not, the test fails, because then evidently we have a bug in our function. So it does not behave like we expected. I talked about mocking earlier, and I want to explain this. In order to, we use mocking in order to achieve test isolation for a test. So the test suite advanced always runs the whole PLC code, so everything. And for our unit testing, we only want to look at a single unit, so a single function or function block that we want to test. And we don't want to have any interference by the rest of the PLC code. Also very important, because a function block saves internal state in its data block, so it's database basically, it's not deterministic. And that means that the same input values could lead to different output values in different calls. Even though I have the same inputs, at the end, we have different converging outputs due to saved internal state that could interfere. And so it could happen that in one cycle of the PLC, multiple calls to the function block take place, which changes the output and then could lead to test failures, even though everything still works as we expected. And to not have interference by any other code in the program, we create a test organization block, or a test OB in short. In the test OB, we call the function, let me take the laser pointer again. In the test OB, we call the function or the function block that we want to test, so that the code that we wrote can interact with it. And OBs are called by the main program cycle directly, so we can be absolutely sure that the functions inside this test OB are called when the PLC is executed. We also create a mock data block, or mock DB, for our values with the same fields as the inputs and outputs of the function. So you can see here input 1, input 2, and output. And these are identical to the function or function block. For a function, then we pass in mock DB input 1 to the input 1, mock DB input 2 to the input 2, and so on, so that everything matches up. For the function block, it's even easier because you can pass the mock DB as an instance DB, and it recognizes the fields and uses the appropriate values directly. So this is even easier. And for this all to work, we need to change the test code as well, because then we have to use the mock DB here. So everything is connected basically. So now if the test OB is run, then we use the mock DB, the values in the mock DB to put into the function and save the output to the mock DB as well. And then we can assert this in the test, and we make sure, so that we can make sure through the mocking that we don't have any interferences by any other part of the PLC. So to summarize, we call the function a function block that we want to test in a dedicated test OB to make sure it always gets called during the test cycle. We use a mock DB so that we control the values of the parameters during the arrange and assert stages. And we have no influence from other calls in the PLC or any internal saved state, because we always use the mock DB. And each test has its own mock DB with the correct fields so that we can have true test isolation. And creating all the mock DBs and adding them to the test OB by hand would be very time consuming, so we can automate this. And the TIA portals offers the TIA openness interface as a way to interact with the TIA portal using the program language C#, which is very handy for a software developer. And using this, you can create an add-in that can be loaded into the TIA portal and then executed from there just by using a button. So we develop an add-in that automatically creates all the necessary mock DBs for us. Creates a test OB, adds the necessary calls, function blocks, and so on, and then passes that to the generated mock DBs as parameters. And it works roughly like I've shown here. We have a function that we saw earlier, and using C#, we can access the interface of the function or we can access the TIA portal and export the function via XML, which is a markup language to transfer data. It's very common, so that we can use it in our C# code. And we read the XML text and parse it to get the information in a format that is very easy to work with in C#. And then we create an empty mock OB class that I created, and create a mock DB class and put in all the necessary data block members. So the input 1, input 2, and output, so that the DB has the fields input 1, input 2, and output. And then we add the function call using the mock DB into the test OB. So yeah, as we saw before, it's just a little too big. That's why I put the 3 dots, but we put the call into the test OB just like we've seen before. And then we export all of this to XML again, which can then be imported into the TIA portal. So with one click of a button, we can generate all the mock DBs and the test OB that then makes sure that everything, if we want to test, gets called. Yeah, and then we can run the tests. To introduce version control, I took the PLC program. We can test it now. We can also generate all the mock DBs and test OBs. And now to add version control, Siemens offers the version control interface, in short is VCI, and different connectors for Git and Subversion, which are 2 softwares for the version control. I use Git to set up a local repository, which is basically just like a directory in my file system. And then I use the VCI Git connector to connect that local repository to GitLab, which is an online platform where you can save and manage your versions on a server. So if I change something locally in my PLC code, or in my test code, or in my SciGuide, I can commit this change to my local Git repository and push that new version to GitLab. And other developers can then pull my version from the GitLab server and work on it further on their own computer, like I showed you before. And usually a software developer interacts with Git via the command line of their computer. And after an initial setup of the Git repository on the computer of the PLC programmer, luckily they do not have to know any of the commands to interact with Git, because in the project navigation in the TIA portal, there's a tab for version control where you can interact with your version and see current changes, and can interact with Git in general just by pressing some buttons that then execute the necessary commands in the background, so you don't have to see any of that. So there's only a small amount of know-how necessary to use this version control in an automation project. So at this point, we can unit and integration test our PLC code, and we can save it on a server using Git. And to run our tests automatically, for every new version that we push to GitLab, we can connect the CI/CD tool to create a CI/CD pipeline and then achieve regression testing. And in my project, I used Jenkins, which is an automation server that can handle many different tasks. And I configured it then to run all the unit and integration tests each time a new version is available in GitLab. So for this, Jenkins pulls the information from GitLab every couple of minutes just to see if there's a new version available. And if it is, then a CI/CD pipeline is triggered, we call it. And then Jenkins opens a new TIA portal instance and connects to a project, loads all the version files from GitLab into it. And this cannot be done just like this. I wrote a C# application for this using the TIA openness interface again, where all of this can just happen, so that I don't have to do it manually, but instead it can just be loaded into the pipeline, and the pipeline does it by itself. So to run the actual tests and collect the test results, there is something called the Siemens Test Runner application, which is programmed by Siemens, and it's executed by the CI/CD pipeline, and it runs all the tests and collects the test results, and then the test results are archived in Jenkins. So in case of test failures, the developer can easily see which tests failed and why. And all with this, we have achieved regression testing, because every time we have a new version, all the tests are run and we have good reliability of our code. in order to implement code coverage, which I explained before, you can simply use the Siemens code coverage add-in from their website. So the add-in can check the code coverage for every component that uses the PLC programming language, structured control language, or SCL, which is a language that looks kind of like Pascal and that was used in software development as well back in the day. And the resulting code coverage report marks every line that is executed and whether or not has been tested, and is therefore covered by unit tests. So you can see here, we have a couple of green lines, and all of those have been covered by unit tests. And then when we see some red lines somewhere, we can see, okay, that line has not been covered by unit tests, and then developers can write targeted unit tests for that specific code section, which is not covered yet. Lastly, the only thing that's missing is as of yet is the system testing of the PLC code on the lower of the upper end of the software pyramid. So for the lower end of the pyramid, we have unit integration testing, and for testing the whole system at the top of the pyramid, we use Siemens SIMET simulation platform, which we can see here. So the PLC code is still in the TIA portal. We then use the SIMET simulation platform to run the system tests, and we execute it again on the PLC Sim Advanced instance on a virtual PLC, as we did before. And the software SIMET simulation platform consists of 3 parts. We have couplings, diagrams, and visualizations. And couplings are used to connect SIMET to other programs, such as PLC Sim Advanced, for example, to exchange PLC input and output signals. And then diagrams are used to model complex processes using a flow diagram, using representations of motors and scales and valves and all of that, as well as logical operators like less than or more than or equal, and also more advanced features like intervals and limiters and ramp functions. So lots of things inside those diagrams, which is the main part of SIMET, so the most important part. And the last thing are visualizations, which are used to display the model process using lines and basic shapes and text that are then linked to PLC inputs and outputs. So for example, if the PLC sets the motor as on bit, then a shape that are linked to the bit moves in a defined pattern. So for example, if the motor for a belt is saying, yeah, the motor is on, then I can have a crate or something move from left to right. And in my project, I used PLC Sim Advanced coupling. So I start a virtual PLC and PLC Sim Advanced, load the PLC code from the TIA portal into it, and then I can control and set the different inputs and outputs from within the simulation platform in the simulation diagram that I've written up. And for the machine in my project, I can simulate, for example, pressure on the scale to test the weighing and the dosing functionalities that I explained earlier when we saw the diagram of how the project or how the machine looks. I didn't actually use the visualizations because I had an HMI available for the machine where I could observe the whole process, and so I just could save me some time and not use the visualizations. So if we look at the results now, we can see that I created the test strategy according to the ISO 29119 with the information provided by a PLC firmware for our client. And with this, I achieved unit integration testing using the TIA portal and the test suite advanced and the PLC Sim advanced for tests that can then be executed on a virtual PLC. For system testing, as I just explained, I am using SIMET for a simulation diagram and to control the inputs and outputs of the virtual PLC. For test automation, I programmed the custom C# application to generate mock objects for the test to achieve test isolation, to not have interference by anything else in the PLC that is running. For version control, I used GitLab to back up the version history on a server so it can be loaded again in the future if required, so nothing gets ever lost. For the CI/CD pipeline and regression testing, I used C#, a custom C# application and Jenkins for automated regression testing after every new version in the version control to make sure that already tested code does not break because of new code that I added. And for code coverage, I just use the code coverage add-in to show which lines are covered by tests and which aren't. So as you can see, I managed to apply the presented software testing techniques for a PLC program using Siemens software, as well as some custom C# code that can then interact with the Siemens TIA portal. For the PLC programmer, the process would look like this. So they write the PLC code, then they generate the mock data blocks and test OB. They write unit integration tests for this, which are then run for the specific PLC block that they wanted to run for, because we have test isolation. They can then push their changes to the version control, where all the tests are always run in the CI/CD pipeline, and can perform manual system tests as well. And if there are bugs anywhere in the process, if they come up, they can then fix the bugs and write new unit integration tests for this, so that the bug or the error cannot occur again. Over time, the software quality improves and less errors can happen, because we always test and add more automated tests as well. However, as I think Dutch programmer said, Edgar Dijkstra, he's called, he said program testing can be used to show the presence of bugs, but never to show their absence. So it's absolutely possible for a tested software to still have some bugs, which is why it's important to continually write new unit tests for found bugs in order to minimize the potential for new bugs. If we look at everything all together, my findings were twofold. There are some positive points and some negative points, as there always are. For the negative points, we have a higher initial time investment if we write tests, because the additional time that is used to write these tests. And in software development, testing can take between 30 to 50% of the development time. And also in the beginning, if you're just introducing testing, the time investment will be higher and then decline up to a certain threshold until the PC programmers get the hang of it and get used to the process and the tools. Test tools like the Siemens test suite also cost money, so it's also a money investment apart from only the time investment, which due to their hourly rates of the employees and colleagues, we also have this additional money investment, because Siemens test suite and Simit simulation platform each cost several €100 per license. And that was really something new for me, because in software development, usually the development tools, including the testing tools or the development environment, are always free and mostly even open source. And then what usually costs money is the specialized support by the manufacturer or anything related to actually developing and running the software, to actually deploying and running the software, so not the development phase. And lastly, the tools are not fully mature yet, in my opinion. And that I had to write a scientific thesis about this is the first hint that, maybe it's not completely mature yet. And in software development, testing is standard practice. Some downfalls of the testing tools were, for example, that they are very restrictive. You cannot run or skip any timers, for example, or set them to a specific time. You always have to follow the arrange act assert pattern very strictly, because you cannot write tests with multiple steps. For example, I cannot set an input, then run for a cycle, set a different input, and run another cycle, and then assert, just to see what happens over the course of several cycles. This did not work with the Siemens tools. And I am also used to pausing the execution while debugging to inspect the current state of variables and inputs and outputs and parameters and so on. And this also doesn't work. Just is not possible with the current test tools. Test tools or test execution also takes a long time, because the whole PLC program is loaded and executed every time, instead of only the function or function block that I want to test actually. Integration with other tools, for example, CI/CD tools, is very inconvenient, which is why regression testing and automated testing is not really that straightforward. And yeah, lastly, there is a small community and small ecosystem because of the pricing, the price point, and that PLC program is not as widely adopted. Maybe also a lot of documentation is only done by the software manufacturer, so by Siemens, for example, in this case, while for software development, it's very usual to go to a website called Stack Overflow, by the way, like Stack Overflow, just because there are a lot of people. They have 23 million registered users, where everyone can submit questions and answers, and it's very easy to find the cause of some problem that you have and fix it. However, we have some positive points as well. For example, the software quality, which there's definite improvement of the software quality through the use of automated tests and programming style guides and the version control. This improved maintainability because of consistent programming styles and distributed backups through the version control. And also the traceability through the version control is, it's way better because evident who did what and why. Next thing is collaboration or cooperation. It's very much improved because people or programmers can work together more easily through version control. And automated tests or automated regression tests prevent code from other programmers, for example, to break my code, because we always test that everything still works for each new version. And if something somewhere does break, the functioning version can always be retrieved very easily. So it's very easy for collaboration. And the last point is the time and cost saving. Sadly, I could not prove this during my project for my master thesis because on the one hand, the client had no metrics for their current process, so they didn't know how long something takes or how much money it costs them. And on the other hand, there was no commissioning of this machine during the pilot project phase, so I could not take any measurements myself. But on paper, testing is definitely possible in parallel. For example, as it used to be, you would program everything, the machine was set up, and then you, after that, you would test on the machine. And right now, because we can test on a virtual machine, you can develop and test in parallel, so there's less time spent. And less time spent always means saving money. There are also less errors during startup on the commissioning of the machine. So that also means less time spent at the customers. So less time spent means less money. And lastly, we have an early detection of errors and bugs, which is proven to have a huge impact on project cost. And I will show you here. The cost of fixing errors over the duration of a project follows the rule of 10. And that means that with every step forward in the process, the cost of fixing an error increases by a factor of 10. So the later in the duration of a project an error is found and has to be fixed, the more expensive it is. So for example, during planning phase, so requirements engineering, architecture, and design, the cost of fixing an error is low. And a lot can be changed or otherwise influenced without great effort. So for example, if we have a bug and we want to fix this here, this maybe costs €1. During the development stage and the associated testing, during the development stage, the cost of fixing an error rises because code has to be rewritten and integration into the system has to be changed or might have to be changed. And it's more difficult to influence the process. And the fixing cost that was be €1 here might be already €10 in the development phase. And then during production, the cost of fixing an error rises again because code has to be rewritten. It has to be loaded on the customer's machine. It would have to be tested that everything works. So the error that would have costed €1 in the planning phase can cost €100 during the production phase because there's a lot more that you have to do in order to make sure that everything still works. So finding and fixing errors as early as possible is of the utmost importance. And the current state of the PLC testing tools and PLC programmers' attitude towards writing automated unit integration tests over manual testing is exactly the same experience that software developers had in the 1990s, because people were very skeptical towards writing automated tests and the testing effort in general. And when Kent Beck, who created the first automated unit testing framework for software engineering, when he introduced the concept to software programmers, he was asked this question: wouldn't it be easier to just do it right the first time? And it definitely would, but sadly, this is just not how developing software works. And yeah, during my project, I was faced with similar questions, and on the internet, PLC programmers are also wondering if automated unit testing for PLC programs is really necessary or worth it. Yeah, and as this evolution happened in software engineering as well, we can look just to see how it played out there. And with the rise of smaller and more intuitive and user-friendly testing tools and frameworks, there was a huge change in attitude towards writing testing, towards writing tests and testing in general between 1995 and 2005, round about there. And today, testing your software is as much part of programming as writing the code itself. So when I was in university, the testing was part of the very first computer science course that I had. And if we look at the current development in automation technology, we see that PLC manufacturers have recognized this trend as well. For example, Siemens has just launched Simatica X, which is a development environment for PLC programs that is very similar to what software developers use. And similarly, Bosch Rexroth launched Control X Automation. Beckhoff has Trinket Cloud Engineering, and they all contain features like unit testing, stepwise debugging, version control, dependency management, and yeah, connecting to CI/CD tools. So in a nutshell, testing your PLC code using software engineering techniques is definitely possible and really can improve your software quality, reduce the risk of errors during production, and also reduce costs. And using the current limited testing tools is very time consuming, but yeah, can still work, as I showed with my project. However, PLC manufacturers have recognized this and are developing more capable development environments and tools, as you can see here. So in my opinion, automated unit testing of PLC code will become the standard in the future, and it has become, as it has become in software engineering years ago, and companies should really be prepared for that. So as I finish up my presentation now, because we are right about at the time, should you have any questions after this hour that we've spent together or want to know more about the conversions of IT and OT, please feel free to contact my colleagues Marco Wanner on the left, or Manuel Achucaro, or myself. We are happy to help you in all your digitalization efforts. So thank you all for your attention and interest. Are there any questions?
Thank you very much, Markus. It was a really interesting presentation. And if any of the assistants has any question, you can write it on the chat or question and answer chat. I'm going to ask you a question concerning the different test approaches defined in the test strategy, and which test techniques is best and which different test types are there.
I explained it on this slide, so the software engineering techniques. So there are loads of test techniques that can be applied. So we have static or dynamic testing, we have black box testing, and under that falls, for example, something called equivalence partitioning. So we have a big range of possible values, and we try to partition it into two different chunks. For example, if we look at all the numbers, we split it up into the negative numbers and 0 to infinity, basically. And instead of testing every single number, -1, -2, -3, and everything that is positive, we split it up, and then we take one of each, for example, and that is then the placeholder for us. And we can say, okay, if one positive number works, then all might work. Or for example, as black box testing techniques, we have boundary value analysis, where we just see if a certain number may rise up to 500, we will test 499, 500, and 501, and then see if the outcome is as we expect. And for white box testing, there are lots of different testing techniques as well. For example, branch testing, where you look at every single decision or branch in your code and always test the control flow and if everything works. Everything works. But not one single one of those is the best. So you just do the one, but instead you always do a combination of different techniques to ensure high reliability, because they focus on different potential errors, and then you have the combination, and through that, your tests are then very reliable, and the software as well.
Okay, thank you very much, Markus. And just a last question. And what is a common code coverage that for a software development project?
Code coverage I explained here, so I just show the slide again. There is no magic number for how much code coverage you need. It's always dependent on the project. So in 99.9% of cases, you don't want 100% code coverage, because that's just way too much work. Because at some points the tests don't make sense anymore, or they are unnecessarily complex to write, and you spend way too much money and time just to have the tests go up, even though it doesn't really have any benefit anymore. So usually in a big and long-running software development project, you aim for about 80%, but there's no fixed number. And for small projects that are maybe not going to be maintained very long, they are written, they are used, and then they are thrown away. You maybe need no tests at all, or just a low amount of tests and test coverage, because you always have to look at the costs and at the savings that you're getting from testing, so that everything is in relation to each other.
Okay, thank you very much, Markus. And I see that there aren't more questions, but if any of the assistants has any question, and we will share with you the Shitaso team's email, so you can write them directly. And well, with this, we finished today's presentation. It was really interesting. And thank you very much to all the assistants, and thank you very much to Markus.
You're welcome. Thank you very much for your attention, for your interest, and have a nice day.
Para estar al día e informados de todos los contenidos y webinars de AFM en YouTube, suscribíos y dale a la campanita.
Elegí el sector del mecanizado porque es algo que me viene un poco de familia. Mi abuelo en su momento también fue calderero, así que sí, conocía el sector de antes. Y es algo que la verdad siempre me ha gustado hacer. El trabajo práctico, la faena manual, ¿no? Lo que es un tema de faenas manuales, siempre me ha gustado mucho.
Bai, bidaiatzea tokatu zait, Europan zehar, egon naiz toki ezberdinetan eta baita estatu batuetan ere bai, eta iruditzen zait oso sektore innovadore eta interesgarria, ze gaur egun mundua dagoen kompetitibidadearekin innovatzen ez baldin badezu ez dago aukerarik aurrera jarraitzen.
Es un sector que ofrece mucha proyección a futuro, ya que pues, te obliga a mirar el diseño desde muchas perspectivas diferentes, no solo desde la perspectiva del diseñador, porque pues luego hay que montar lo que diseñas, y a mí pues me gusta mucho el hecho de que tú diseñes algo y tus ideas se plasmen luego en el taller y verlas cómo se convierten en realidad, y pues la verdad que eso yo creo que te da una perspectiva muy amplia y te da pues, mucha proyección de futuro.
Sí que toca viajar bastante, sobre todo dependiendo de los proyectos en los que estés involucrado y si estás haciendo una tesis. Y sobre las reuniones de proyectos normalmente suelen ser más a nivel de gestión, dependiendo del consorcio pues suelen ser o nacionales o internacionales, pero en general sí que suele tocar viajar.
Es fundamental el querer aprender, el querer formarse, el querer siempre ir un paso más de este trabajo, sobre todo, que hay que estar muy informado, hay que cada día formarse más y tener mucha actitud para poder estar a la altura del puesto.
Sektore honek nire etorkizunerako oinarri oso sendoak dizkit ematen eta diseinatzaile bezala asko hain ez ikasten, eta nire etorkizunen ere diseinatzaile bezala lan eta gustatuko zaiten sektore honetan edo beste baten. Nire perfileko pertsona batei esango nion karreran zehar gauza industrialak eta gustatu izan baldin zaizkio, dudarik gabe sektore hau gustatuko zaiola eta ikasteko gogokin etortzeko eta pozik egongo dela.
Creo que hasta ahora ha sido un sector bastante clásico, pero ahora está dando a grandes pasos muchos cambios, y la innovación y tanto la inclusión femenina se puede ver cada día más en los talleres y en este tipo de sector. En este sector soy feliz porque creo que estoy creciendo tanto personalmente como profesionalmente y puedo emplear todos los conocimientos que he recibido hasta ahora en la universidad.